Okay, so today we're going to be going over some problems involving specific heat capacity and specific latent heat. I know these calculations are probably new to you, and so I'm just going to go over some more examples and maybe one or two problems from the worksheet, just so that you have a better understanding of the concepts involved in these problems, because it's really important that you understand the concept of all of the calculations that you're doing. Okay, so this first question is not a calculation question, it's a concept question. You see these all the time on the IB exam where you actually have to explain something in words. Okay, so take a look at this question. It says a small piece of ice is placed in a cup of warm water. The temperature of the water decreases. And the two questions are explain how the internal energy of the water changes as it cools, and explain how the internal energy of the ice changes after it is placed into the water. Now, when you have an explanation question, you need to write in complete, coherent sentences with correct grammar. These explanation questions typically are 2 to 3 points, which is actually quite a lot on the IB exam, and you have to make sure that you answer the question fully. So as I'm reading this question and I'm trying to figure out, where should I start on this question, the first thing I'm going to notice is the question says, explain how the internal energy of the water changes. So number one, I need to know what internal energy of the water means. And number two, I need to write that out so that the person reading it knows that I know what internal energy of the water means. So remember, the internal energy of a substance is basically the internal kinetic energy of the atoms or molecules making up the substance plus the internal potential energy of the atoms or molecules making up that substance. Now make sure that you mention the atoms or molecules. In this case it would be molecules because water is obviously made of H2O molecules. But you have to reference that. You can't just say, oh, kinetic energy plus potential energy. No, that's not what it is. It is the kinetic energy of the atoms, or the kinetic energy of the molecules, plus the internal potential energy of the atoms or molecules. Now, nobody's asked this so far yet, but a good question to ask would be, what type of potential energy is there in the atoms or the molecules? Because it's obviously not gravitational potential energy, and it's not something we're going to go into detail about, but it's actually electrical potential energy, because because molecules and even atoms in a solid, liquid, or gas are held together by electrical forces because they're charged particles, and so we're not going to go into any detail about that, but when we talk about the internal potential energy between the atoms or molecules in an object, those potential energies arise because of electrical forces, and that's, again, not something we're going to talk about. It's maybe more complicated than we need to get into now, but in case you were wondering, that's what that is. Of course, kinetic energy is the kinetic energy we learned about in the last unit. That's just 1/2 mv squared. But in any case, we need to say something in our explanation about what internal energy is. Okay, so if I was writing this out, I would maybe have a line in there about, okay, so the internal energy of the water molecules, the internal energy of the water is the total kinetic energy of the water molecules plus the total internal potential energy of the water molecules. And that would be my first sentence. Because if I want to explain the actual answer to the question, I need to start with what is internal energy. That's just, a good writing strategy. If you're asked to explain something, you should start by defining what that thing is. Next, you need to actually answer the question. Okay, so saying what internal energy is just generally doesn't answer this question. It's maybe 1 point out of a 3-point question. Okay, so as the piece of ice cools, obviously what's going to happen to the water is the water is going to cool down, because that's what ice does. Now, the water is not going to phase change or anything, and so what's going to change with the water is that because the temperature of the water is decreasing, that means the average kinetic energy of the water molecules is also going to decrease, because the ice is going to cool down the water. Okay, and so that would be the second, possibly third point in your explanation. Now, the water is not going to phase change, and so the only thing that's going to change is the average kinetic energy of those water molecules. Now, in the second question, if you had a question like this, 2 explanation questions about internal energy back to back, you would not have to define internal energy twice in a row. That doesn't make any sense. But the second question says, explain how the internal energy of the ice changes after it's placed into the water. Now, the ice is a little bit different. because the ice is going to go through stages. And so assuming that the ice is at 0 degrees Celsius, which we don't know if it is or not, but if it is, the first thing that's going to happen is if the ice is at 0 degrees Celsius, that's the melting point of ice, the first thing that's going to happen to the ice is it's going to phase change. And phase changes are associated with a change in internal potential energy. Okay, so your first sentence might be something like, as the ice melts or undergoes a phase change, the internal potential energy of the water molecules is going to increase. Okay. Now I know it's going to increase because when ice melts into water, the overall internal energy is going to go up because you have to add a heat into ice to make it melt. Okay. And so even though the temperature of the ice doesn't change during a phase change, the internal energy still does. It increases. It's just that it's only the internal potential energy part that changes. Now, once the ice melts, what do you have? Well, now you have warm water mixed with very cold water, right? Because melted ice is after it melts. So let's say after melting, what do you have? Well, you have water at 0 degrees Celsius. So what's going to happen if you have water at 0 degrees Celsius mixed with warm water? Well, eventually, they're going to reach thermal equilibrium. Okay, and so I would say, for the first part, I would say as the ice melts and undergoes a phase change, the internal potential energy of the water molecules increases. After the ice melts, the melted ice reaches thermal equilibrium with the warm water, and so the average kinetic energy of the melted ice molecules is also going to increase. In other words, there is going to be a phase change plus a temperature change. Okay, and so the internal energy is going to increase in two regards. The potential energy of the molecules is going to increase, and during the temperature change, the average kinetic energy of the molecules is going to increase. Okay, so that one is maybe a little bit more involved. I would say if this was an IB question, this is more like a 2-point question. This is maybe like a 2 to 3-point question. Okay, but you need to use complete sentences. You need to answer the question fully. When you're doing a problem and you look at the point value, that should kind of guide you in what level you have to go through to answer the question. Now on the next slide, I actually have the answer that I typed out. Not to say that it's a perfect answer or anything, but it does, I believe, answer the question successfully. So pause it here if you need to. Maybe type out your own answer and see if you could come up with something similar to what I come up with. And then on the next slide, we'll see what I put. Okay, so this is the answer that I came up with. Internal energy is the total kinetic energy, or the total kinetic and potential energy of the water molecules. As the temperature of the water decreases, the kinetic energy of the molecules decreases, and the potential energy of the molecules stays the same because the water does not change its phase. Okay, so that's my answer for the first one. For the second one, after the ice is placed in the water, the potential energy of the ice molecules increases as the ice melts. After the ice melts, the kinetic energy of the molecules increases as the melted ice and water reach thermal equilibrium and reach the same final temperature. Okay, so I believe that these two combine to fully answer the question. Okay, so this is not a calculation question, but you still need to be able to do this type of question because concepts are important. And you're going to see more and more explanation questions as we go throughout the semester. Okay, so the next problem we're going to do is a problem similar to the problems that you saw on worksheet number 5, and it's going to be done in multiple parts. So it says, calculate the heat absorbed by a 1 gram ice chip as it warms from negative 15 degrees Celsius and then melts completely. And then the next part of the question is saying, assuming this ice chip is placed in a 10 gram cup of coffee with an initial temperature of 50 degrees Celsius, calculate the temperature of the coffee. Okay, so we're going to do this first part first, okay, and then we'll see what happens after we put the ice chip into the cup of coffee. Okay, so calculate the heat absorbed by 1 gram ice chip as it warms from negative 15 degrees Celsius. So I'm going to go over here. I have my mass of the ice. M ice is 1 gram. Now that is 0.001 kilograms. Don't forget to convert as necessary. I'm given the specific heat of the ice is 2100 joules per kilogram per Kelvin. I'm also given the latent heat of fusion of water is 3.34 times 10 to the 5 joules per kilogram. And the first question basically just says, what is the heat absorbed by the ice when it goes from negative 15 degrees Celsius and then it melts? So the first thing I'm going to recognize is, well, ice does not melt at negative 15 degrees Celsius. And so I've had a lot of people ask me, how do you know how many equations to use? How do you know how many steps that are in your problem? Well, you just have to go sequentially, and you have to think through each problem individually. Go in order. Now, if I'm thinking of this ice chip, and I'm thinking, what is the ice chip going to do when I add heat to it? Okay, well, it's not going to melt because ice does not melt at negative 15 degrees Celsius. And so the first thing that this ice chip is going to do when I add heat to it is it is going to, let me turn my pen back on. It is going to temperature change, okay, and that's going to be given by MC delta T. Now, what is it going to temperature change to? The initial temperature of the ice was negative 15 degrees Celsius. Okay, what is the final temperature of the ice going to be after it melts? Well, ice melts at 0 degrees Celsius. That's something you have to know for this problem. If it was something other than water, you would be given the melting or freezing point or whatever else you needed. But water is assumed that you know that water freezes / melts at 0 degrees Celsius. Okay, and so that's going to be the final temperature of the ice. Now, this is not including after we put it into the cup of coffee. That's a completely different situation. Remember, this is actually 3 different problems, right? There's this first part up here that's just the ice chip by itself, and then there's what happens after we put the ice chip into a cup of coffee. Okay, so we're still in the first part. So the first thing that's going to happen when we start to melt the ice cube is it's going to temperature change up to its melting point. Then it is going to phase change, and the heat required for phase change is given by mL, right? The mass times the latent heat. In this case, the latent heat of fusion because the ice is melting. Okay, so since we have the values given to us, we can easily do this calculation. This is the mass of the ice. Okay, so 1 gram converted to kilograms times 2100. Delta T is going to be the final temperature minus the initial temperature. Okay, so that's our MC delta T term, plus the ML term, which is 0.001 times 3.34, so 4 times 10 to the 5, and I'm just going to write that out with my calculator. The first term is going to be 31.5, and then the second term, 0.001 times 3.34 times 10 to the 5 is going to be 334. Okay, now normally I would have just added those two numbers together in my calculator, but I wanted to write them out just so you can see the difference between them. Right? Notice that it takes way more heat to do the phase change than it does to do the temperature change, and that's generally true. We talked about in a previous video about why it hurts more to get burned by steam versus an equal amount of hot water. That's because there's way more energy typically in a phase change than there is in a temperature change. And this is in joules. Now this is the heat absorbed by the ice right after it melts. Okay, so the heat required to get it up to its melting point and then to actually melt it. And so I'm just going to write that down because we're actually going to need that for the next question. Okay, now again, we have not put it in the coffee yet. We're about to put it in the coffee here in just a second. So let me do that now. Pause it here if you need to look at this. Okay, so now I place it in a cup of coffee. And the cup of coffee has a mass of 10 grams. I'm given the initial temperature, specific heat capacity of coffee, and I want to know what is the temperature of the coffee at 2 different times. Once right after the ice chip melts, and then again after the ice chip has reached thermal equilibrium with the coffee. So a lot of people have asked me about worksheet 5, question 5. Okay, what's the difference between 5b and 5c on the worksheet? And the difference is 5b, you're adding steam to milk. In question 5b, the steam after it turns into water, after it condenses, it's not yet in thermal equilibrium with the milk. Okay, and then 5C, you're assuming it is in thermal equilibrium. And so this is a very kind of analogous problem to that. Okay, so first I want to know, what is the temperature of the coffee right after the ice chip melts? Anytime you have a two-object problem, and this is obviously a two-object problem because I have the ice chip in the coffee, you're going to be doing it with Q in equals minus Q out. Okay, now, if you get confused, what goes on which side, you just have to think, which is the cooler of the two objects here? Okay, whatever is colder is going to be the Q in, because heat always goes from hot to cold naturally, and so the Q in side is going to be the side that was colder to begin with, so in this case the ice. On the right side we have the coffee, so that's going to be minus Q out. Now I need to break down what's going to happen to the coffee when I put the ice chip in. Do we think that the hot coffee is going to phase change? Probably not. Okay, what do you think the first thing is going to happen when you put ice in the coffee? It's going to cool down. It's going to temperature change. So that's going to be just an MC delta T. Now, I guess technically speaking, I don't know if it's going to phase change or not. I'm just going based off of assumptions. It's entirely possible to do this problem and come out with an impossible answer, because it turns out that there should actually be a phase change here as well. I'm just relying here on common sense that when you put a small piece of ice in a cup of coffee, it's probably not going to turn the whole cup of coffee into ice. Okay, so I'm going to assume that the only thing that happens on the right side, the coffee side, remember this is the coffee side, and then the other side is the ice side, right? Because the coffee is hotter to begin with, so heat is coming out of that side. I'm going to assume the only thing happening to the coffee is a temperature change. Now, I'm going to do this for question 1, or I guess technically question 2, because this down here was the answer to question 1. I'm going to assume that for this question, we want to know the final temperature of the ice, or the final temperature of the coffee right after the ice chip melts. And so we have minus, now 10 grams, you have to convert that to kilograms, of course, so that's 0.01. Is that correct? Let me just double check. Yes, that is correct. The specific heat capacity is given in the problem as 3980. And now, no matter if I'm talking about question 2 or question 3, I'm still going to have the same kind of setup on the right side of the equation. I have delta T, which is T final, which is my unknown, and the initial temperature of the coffee is given as that. Now, Q in depends on if we're talking about question 2 or question 3. Question 2 is right after the ice chip melts. Question 3 is after thermal equilibrium is reached. Now, right after the ice chip melts, remember, in order to get the ice chip to melt, first we had to have an MC delta T term. Then we had to have a phase change term. Now, if I wanted to go all the way to thermal equilibrium, I would have to add a third term on the left side, another MC delta T term, to get that melted ice, which is now water, up to thermal equilibrium. Now, I'm not going to do that until question 3, but you can have like 3 or 4 or 5 terms on this side of the equation if you need to. Now, I'm also not going to write out what these values are because I actually know what this number is, because I had to find it for the last question. Right, that's that 365.5 joules. That's just the heat required just to get the ice chip up to its melting point and then to melt it. So for question 2, I actually know that the left side is already this value. Of course, if you didn't know that, you could just plug in values and figure it out. On the right side, I have minus 0.01 times 3980 times TF minus 50. And then you just need to do a little bit of math. I need to simplify what's on this side. That's going to be 3980 TF. Don't forget to distribute this minus sign. This minus and this minus are going to cancel. Okay, and so I'm going to get plus 1990. And when you do the algebra to work this out, I'm just going to save you the steps and do the couple remaining algebra steps in my calculator. You should get TF equals 40.8 degrees Celsius. And again, this is for 2. Okay, so this is not the thermal equilibrium temperature, but this is just the temperature right after the ice is melted. Okay, so pause there if you need to look at that. Okay, now I'm going to erase some of this, and I'm going to do the last question. Okay, so I'm going to erase this bit over here. Now, it's still a two-object question, but now I want to go all the way to thermal equilibrium. Okay, so the setup is the exact same. The only difference is if I want to go to thermal equilibrium, remember that on the right side I have the MC delta T for the coffee. Why do I only have one thing on the right side? Well, because the coffee is only going to do one thing. The coffee is only going to temperature change. It's not going to phase change. Now, how do I know that? Well, again, just kind of common sense. I mean, it doesn't have to be that way, but it is for this problem. So I already know that this is going to be the mass of the coffee times the specific heat capacity of the coffee, which is 3980. Let me erase that. I don't know what I'm doing here. Running out of space here. 3980 times T final minus 50. Actually, let me move this over so I have enough room to write. This is going to be MC delta T for the coffee, sorry, minus MC delta T for the coffee, 0.01 times 3980 times T final minus 50. And on the left side, now I'm doing question 3. Okay, so remember the left side is the heat for the ice. Now what's going to happen to the ice? Well, if we're going all the way to thermal equilibrium, again, you have to do this in stages. You have to start at the beginning. When we first add heat to the ice, what's going to happen? Well, the ice is going to temperature change up to its melting point. Now, what's the next thing that's going to happen to the ice once it gets to 0 degrees Celsius? Well, it's going to phase change. Okay, what do you get after you phase change ice into water? Well, you get cold water. What is that cold water going to do when it's mixed with a hot coffee? It is going to temperature change. Okay, and so now we have 3 things on the left side of the equation rather than 2. Do keep in mind that even though the mass is the same for everything in this problem, this C and this C are not the same because this is for the ice, this is for the water. Okay, because once the ice is phase changed, it has become water. And so we're going to have to use a different specific heat capacity for this C right here. Okay, so now I'm just going to, well again, the first thing I'm going to do is I'm going to have the mass of the ice times the specific heat capacity of the ice, 2100, times 0 minus negative 15. You might say, well, wait, shouldn't it be T final instead of 0? No, because the ice does not go past 0 degrees Celsius. The ice, it stops being ice after 0 degrees Celsius. So the temperature change for the ice hasn't changed. Okay, neither has the other term, the ML term. We have 0.001 times 3.34 times 10 to the 5. Okay, those two stay the same, but now I'm doing this last MC delta T term. Okay, so I have 0.001 times the specific heat capacity. Now this is water and not ice, so I have to use 4200. It's not given in the problem, so I'm just going to use 4200. 4200 is the specific heat capacity of ice times delta T of, 4200 is a specific heat capacity of water, times delta T of the water. Now, I don't know what the final temperature of the water is, because that's when it reaches thermal equilibrium with the coffee, but I do know that the initial temperature is, well, let's think about this. When does it become water? Well, after the ice is melted. What is the temperature of melted ice? 0. Okay, so the initial temperature of the water on the left side is 0 degrees. And on the right side, I have the same thing, and I'm just going to simplify that out. 39.8 times T final minus 50. So nothing has changed. Sorry, there should be a negative sign here. Nothing has changed on the right side of the equation. Okay, now there's a lot going on, so I'm going to erase a little bit, just so we can finish this problem up. Pause here if you need to. Okay, so I'm going to just give myself some space up here by erasing some of these things. Okay, so on the left side, I'm just going to calculate all this out. I'm going to do 0.001 times 2100 times 15. Okay, so that's going to be that 31.5 plus 0.001 times 3.34 times 10 to the 5. That's going to be my 34 plus 0.001 times 4200 times TF. Okay, I don't need to worry about the 0 because 0 times anything is 0. So I'm going to get 4.2 TF. And all of that is going to be equal to minus 39.8 times TF minus 50. I would not normally write it going down like this. I'm just kind of running out of space. So I'm trying to do the best I can. So imagine these three things being added together on the left, and then on the right it's equal to this right here. So from here, we're just going to simplify it like terms. Now 31.5 plus 334 is 365.5. I cannot combine that with the 4.2 because they're not like terms. Okay, so this is my left side right here. And then on the right side, I get negative 39.8 TF plus, I say plus because that negative sign is going to distribute, 39.8 times 50 is at 1990. I'm just going to kind of box this out here. Sorry, I'm running out of space here. And then this is my equation that I want to solve right here for TF. I can easily do that. That's basic algebra. I move this 39.8 TF to the left. I subtract the 365.5 on the other side. If you do that, you should get, let's see, 4.2 plus 39.8 is 44 TF is equal to 1624.5, and so TF is equal to 36.9 degrees Celsius. And this is the final problem on this slide. Okay, so now the piece of ice has reached thermal equilibrium with the hot cup of coffee. So hopefully you have a better understanding of how to do this type of problem. I know that was kind of a lot going on, and I wish I could do more examples like this, but just in the interest of time, I don't really want to. Maybe in other videos, if there's still some confusion, I might do 1 or 2 more examples with calculations, but hopefully that gives you a better understanding of how to do these multiple step 2-object problems. Okay, remember all 2-object problems, you're using the concept of Q in equals minus Q out, that conservation of energy idea. The idea that all of the heat coming out of one object is going into another object. And then from there, you either have an MC delta T term or you have an ML term. You can't have both at the same time. It kind of goes in order. Okay, and so you just kind of have to go step by step through the problem. So hopefully that helps. If you have any other questions, please let me know by email. I'm going to stop here. In the next video, we're going to go on to the next part of this unit. So please definitely make sure that you complete worksheet number 5 and that you ask me if you have any questions. Because it's really, really important that you understand how to do these type of calculations. They're not hard once you figure out the concepts, but they do take a little bit of practice. So please let me know if you have any other questions.